today's date. Valero mechanical principles. Today's date is the 23rd of the 10th. Actually, I don't like it like that. Let's do it like this, because I end up doing. Right. I think you've all uploaded the beams. We've done beams. Everybody okay with beams? Did everybody upload that homework? You should be okay now. We're doing. You should be okay with doing one like that. Alright.
Sorry to interrupt, man. Where did we have to upload Nigel's work to?
Is my name Nigel?
Anyone? No.
Oh, you're not talking to me. Okay, sorry.
I'm asking the question. Yeah.
Sorry.
If you're on the health and safety page, just scroll down. There should be like.
I can see on there, man.
Have you clicked on like the go on Moodle? You know when you click on like the subject.
Yeah, health and safety.
Yeah, click on health and safety. It should be there when you go down. Then.
It's called Submit October Worksheet here.
Yeah.
It's very precise, isn't it?
Well played.
Open your eyes, John boy.
Kieran, since you got a name on the park, you've got all these chops in you. I hope your fucking PlayStation breaks.
Right, in your assignment, you should be okay now with doing a beam with forces and UDLs. Does everybody agree with each other? Is everybody happy with the beams? Let me know if you're happy with beams.
When you're going to teach us about the beams, Mugs?
Shut up. Look what colour that is. Look at that lovely colour. All happy. Okay, well done. Heather's happy. Anybody else happy with the beams? Because I'm going to move on now. I'm going to move on. Just in case I don't have you next week. But I won't let you, I won't spread that rumour. Right then.
Well, I need a pen and paper today.
No, you're a volunteer. You volunteered to be here. It's up to you. Yeah, I would say so. Yes, I would. Yeah. Obviously, I'm recording this video, John, because I worked out how to do it properly now. Because I got a few videos where there's no sound, so. And I'll screenshot as I go along, so I'll make this stuff here now. All of these notes, I'll just make like a PDF out of it. I'll screenshot at the end of it and just cut all the images into notes for you. So you haven't. I would write things down. That's how the brain works, really, innit? Goes in. But yeah, I would, John. Right. So okay with beams then. Okay with beams. New subject then. No, it's not new to us because we've done a bit in materials. New subject. Not new because we've done a bit of it already. We've done a bit of it already. If you've got, right, if you've got a bit of metal or a bit of plastic or a bit of whatever, right, whatever this is, we know it's got, there's the area, right? So it's just, this is very similar to mechanical materials. That's my area, that little rectangle. If I now apply a force this way, there's my force. Right, going that way. What type of force is that called? It begins with T. What do we know? You've heard the word before. Tensile, it's in tension. And all that means is being pulled apart. So tensile just means it's in tension, it's being stretched, say. That's all it means. This metal bar, or whatever it is, has been pulled apart. So it's in tension. We can have the same thing applies the other way. Here's my round bar. The area, as we know, is the area of this, the cross-sectional area, so the area we use. So that round bar could have a force going this way as well. So you can have one going one way and one going the other. What type of force is that? It begins with C. And we know, begins with C. Compression. So that's in compression. And if you want to use like a word for it, right, it's been squashed, right? Don't use that word because it's not very good. Right? So this one here, component A is being pulled apart and component B is being squashed. Right. Now, as with everything, we'll have a length. So this could be length here and here. That's my length. Here, and this could have a length here and here. In component A, it's being pulled apart. So is the length going to go up or down? Right. Obviously, in tension, it's being stretched. So the change in length, like we've been sort of talking about, is going to change like that. Right? So this here we'll call X. Because X is extension. It's been pulled apart. Some people, you will also see, and I will use it from now on, X, right? And all X means is it's change in length. I will use this from now on sometimes. Delta L. Delta just means change in. Right? It's the same thing. Use X if you want to. If you see me using triangle L, delta L, it just means change in length. So if you see delta T, right, that just means change in temperature. You don't need to write that one down. But delta T just means change in something. And this thing is being pulled apart, so it's changing length. You can either call it X, right, because it's being pulled X millimeters or X meters. But you may also see delta L. Obviously, this one with the compression is going to go the other way in it. So it's getting thinner. It's being squashed. So it's going from, it's like a can crusher. It's going from that to that, say. Yeah? So this is my change in length, delta L. I'm just squashing it. Huh? I'm squashing it. Squashing it. One's going one way, compression's going the other. So a lot of rugby players, they have, compression in the neck. They, squeeze your neck into your spine, right? Compression. One's getting thinner and one's getting fatter. Because if I pull this apart, component A is going to get thinner because it's going longer. It's going to get long and thin. And component B is going to get short and fat because it's been squashed. So the length is coming down, but its diameter is going up because it's got to go out. So you will find this. So tension tends to do this. Tension will tend to make things go from, say, like that. It's being pulled, so it's getting longer, but it's getting thinner. Because the force is going that way. Alright, and it's going to get, so it's all the materials going up. So it's getting longer and thinner. Now we only consider really the change in length in one direction. We only consider it in one direction because obviously it's changing length there as well. But that's another subject. So tension is getting long and thin. And then the other way then is this. So this is compression. Compression. If you have something like that, whatever it is, there's your force. Alright, it's going to go like that. Really, the length is going to squash it. It's got to go. It's getting thinner. It's getting smaller but fatter. Tension and compression. We only worry about for now the change in length in this direction, up or down. Right. Change in length in the Y direction, because this is Y. That's Y and that's X. So it's uniaxial. Uniaxial, what does the word uniaxial mean? Uniaxial, right? What does the word uni mean? Unicycle. One axial means one axis. So we're going in the Y axis. So it's in the Y, right? Obviously, this one's obviously in the X axis. This one is in the Y axis. All it is just go in, right? We're not considering the change in length in the other way. Is everybody right so far? Type a dot. .con. Just see if I'm still on the go. Yep. Right, obviously, when I pull something apart, so when I pull this thing here apart, we'll do tension first. It's the same formula for compression. When I pull this metal block apart, right, there's my area. Right, it's always the cross-sectional area. Right, if you cut it in half, that would be the area there. That's the area. Right. Don't do volume, do the area. And this is length. That's length. So if we've got a force going this way, there's my force in newtons. It's going to make this thing change in length. I'll just draw it like that. Delta L just means change in length. All right. Or X, it's up to you. You can call it X if you want to. As long as you know what it is. L is my original length. Original. And then this force will tend to make this thing stretch depending on the force and the area and whatever and the material. It'll make it change in length. In tension, it's going to stretch it. So we can work out, like we've done before in material, sort of, we can work out the stress, right, in the bar, in the material. Just like you feel stress, right? We can work out the stress in the material due to the force, due to the applied force. Now you recognise the formula for materials because we've used it to work out yield, stress and things like that. But a force will cause a stress. All right? A force, there's my force, it'll cause a stress. All right? Which also causes a change in length. And depending on the material, it could snap, could reach the yield point or the breaking point. But to work out the stress in that bar, or whatever it is, 3, 4, to work out the stress in this bar, the tensile stress is going to be, because we're in tension now, right? Tensile stress equals, you've seen it before, force over area. If you can write anything down, John, write that down. Tensile stress is force over area. You've seen that before, materials, perhaps? Obviously, force is measured in newtons. Area is measured in square meters. So you could use that as the unit if you wanted to. We tend to use Pascal, PA, Pascal. But newtons per square meter or a Pascal, same thing. Because it's a newton over a square meter. That's why you've got to be in square meters. That's why I'm dividing areas by 1,000 or dividing lengths by 1,000. So the unit is either newtons per square meter, like that, do like that everyone too, or Pascal. You'll see both being used depending on where you are. Obviously, you have the same thing then for if it's going the other way. We'll also have compressive stress. Right. For now, we'll just consider it to be the same because it's got a different direction in it, really. Compressive stress is still force over area. It's the same formula, it's just a stress. Force over area. That's also measured in newtons per square meter or Pascal. If you do HNC, right, obviously tensile stress is going that way and compressive stress is going that way. So we haven't got to do it this way, but in future you may. One is positive and one is negative. One's going to cause extension, one's going to cause compression. So this is the same formula. Uniaxial. It's uniaxial. It's different if you're going to use 2D. Because we're only doing one direction. It's only one direction. John's favourite band.
Why have you only put PA, not Pascal, on this one? Does this stand for Pascal, yeah?
Yeah, PA stands for Pascal, yeah. So you can write Pascal if you want to. But just do PA. Capital P, small a. Mathematician, Pascal was, yeah. You can write Pascal if you want to, John, but most people just write PA. We're only doing one direction, so I don't want to confuse you too much. Because don't forget we've got 3 directions. Well, depending on what you think. So don't forget the area is this cross-sectional area in there. It's that area there we're talking about. In there. In this case, it's the area of that rectangle. Width times height. And you may have a round bar like this. So there, like we've done previously, materials can be pi r squared or pi d squared over 4. Whatever you want to do, right? Obviously, our...
Mold.
Yeah?
Is it possible for you to make a savable?
No, what I'm doing, Connor, I don't know why I didn't think about this previously. I got PowerPoint on this, Connor, and things like that, right? But what I'm going to do is now I'm screenshotting this on my Apple as I'm going along,
Yeah.
and then I'm going to make it into like a PDF and upload it.
So can we download it then? Yeah.
It'll be on Moodle then, yeah, with this video as well.
Okay, cool. Cheers.
So don't say anything like Git, because it'll be recorded.
How do you look up the area? Did you say that?
We'll come now in a bit. We'll come in a bit, right? Right. Don't forget now, right? The length, right?
Don't worry, I just remember how to do it.
Yeah, we'll do it now with it. If I've got, if I've got this cross-sectional area like this, so this could be my height and this could be my width, say. So it's that's that area of that square, that rectangle. You may have these lengths in millimeters, right? But we don't want to be in millimeters. We want to be in meters. Right, so you'll see me convert these two. You've got to convert before you do anything else. So 3 millimeters and 2 millimeters, because we're not going to get bits of metal with meters, because that's going to be too big. So you make it dimensions in millimeters. So obviously, to work the area of that out, that rectangle, is just going to be 3 times 2. 3 times 2 is 6. Well, that's going to be in square millimeters. So you got to convert. So you've got to convert, you've got to do this. The long way doing it is 3 divided by 1,000 times by 2 divided by 1,000. That's what you've got to do first, right? You've got to convert the lengths into meters. And there's 1,000 millimeters equals 1 meter. So you divide it by 1,000. Divide the 3 by 1,000, divide the 2 by 1,000. That will give you 6 times 10 to the minus 6. That's what you'll see me doing in a bit, right? Because make sure you've got to convert things. Don't divide the 6 by 1,000. Don't divide this area by 1,000. You've got to divide the length by 1,000. Alright, because we've got to be in square meters. That's what we've got to be in. To be in pascals. Now obviously American is going to be inches and square inches and things like that. But just to get used to it, right? I mean, you can quickly do it, but so on your calculator you'll see that as well. You'd see 10 times, x times to the x. It's normally done by the equals button. On here, look. I'm gonna get this up. There, look. Here, look. Here. There, look. There. Can you all see that? You can't, can you? No, you can't, can you? I'll share my screen. Yeah, let me share my screen. Actions. Take presenter. Share your screen. Share my screen. Share. There, look. So if I got 3 millimeters, right, just so you know, if I got 3 millimeters and I want to make that into a meter, all right, you can do this. 3 divided by 1,000. All right, that gets it into meters. Press equals. All right, or you can just do this. 3 times 10 to the minus 3. 3 times 10 to the minus 3. So that's what I'm doing. I'm converting millimeters into meters. So you'll see that in a bit. Right, I'll give you an example. We'll do an example. Everybody right so far? I'll do an example and then it makes it a bit easy then. Obviously, we're only going to get like, squares or rectangles and circles. So all you need to remember really is the area of a circle and the area of a square. Now, what page are we on? Page 6. Page 6. Page 6. Here's my example, right? Here's my round bar. Here's my round bar. It's got a diameter, right, which means there's my area. It's got a diameter diameter equals 7 millimeters. Alright, so we can work out the area in a bit. It's being pulled apart by a force. It's a environmentally friendly force, that's why it's green. Alright. Somebody give me a number. Somebody give me a number. 8. Alright, so need to calculate in a bit. So 8 kilonewtons is pulling this thing apart. Connor, you can do that one, Connor. You can do yours. Right, it's been pulled apart by 8 kilonewtons. We need to work out what is the stress, the tensile stress in that bar. Tensile stress equals don't know. All right, it's in tension, so it's going to be tensile stress. So we'll do this. So we know that stress equals force over area, because that's what it is. So we know the force. The force is, don't forget, now don't do like some people did this morning and put 8. The 8 kilonewtons means is 8,000 or 8 times 10 to the 3. Because kilo, that's 8,000 really. Or it's 8 times 10 to the 3. Make sure you don't forget the K. That's our force, easy when you've done it, right? Easy, 8 kilo. The diameter is 7 millimeters. We need to work out now the area. 2 ways you can do area. I prefer this one, pi d squared over 4. Or you could do area is pi r squared. Do it the way you want to do it. I will do it this way because this is the way to do it really. Saves you having to divide that by 2. You may forget. You may forget. So don't forget we need to convert this 7. Right, so this 7 now is going to be 7 divided by 1,000 or 7 times 10 to the minus 3 because we've got to be in meters. So area, I'll get my calculator up in a bit, right? But we'll do this now. We'll do pi times by 7 times 10 to the minus 3. Square it. Right? Don't square both. It's the d squared. All divided by 4. That'll give you a number. And if you're going to use pi r squared, right, you should get the same answer. Times pi times by half of 7 is 3.5. Squared. Don't forget the square. People forget squares all the time, right? So it's up to you which way you want to go. You get the same answer either way. I'll share my screen, share my calculator. Share my screen. Yes, share calculator. Oh, I can't remember what it was now. So it was 7, wasn't it? Was it 7? It was 7, wasn't it? So we had 7, so the area is going to be this, right? So we're going to have, so we could do all in one go if we want to. So we could do this. We'll do 7 times 10 to the minus 3. And it was d squared, so we can do, we'll square it. Equals that, times by pi, shift pi, divided by 4. So that's the area, 38.48. Or you could do pi r squared, it's up to you, pi r squared. So we could do this, and we could do shift, we could do pi times by 3.5 to the minus 3 squared. Pi r squared. You may like it that way, it's up to you. Pi r squared. Get the same answer, look. We don't like minus 5s. Let's put E and G. 38. 38.5, say. Is everybody okay with areas? You okay, John? Is everybody all right? All right, John? John, are you okay, John? Because I know you were asking earlier on.
Yeah, man.
Okay, 38.5. I'll use N 38.5, right? Stop sharing. So either way, where's my pen? Either way, you get 38.5. 38.5. I'll round up, look. Don't forget times 10 to the minus 6 square meters. Square meters. That's my area, and this is the area you want to put in here. 38.5 times 10 to the minus 6. Let me get a bit of a pen, because once I share my screen, I can't see that. So that's what you want to put in your calculator now. Is 8 kilonewtons divided by all that area, and things are falling apart on me. So we're going to do 8,000 really divided by all of that, and you should get, I'll do it on the screen, I'll do it on here, just so you know. Share my screen. I should do like counters really. Calculator, so it's going to be 8,000 or 8 times 10 to the 3. Oh, let's do this way. Right, 8 times 10 to the 3 or 8,000 divided by the area which I rounded up, 38.5 times 10 to the minus 6. Press equals. It's going to be a big number. That's the answer. You can put all that in if you want to, or you can put in that. 207.8, something like that. 207.8 times 10 to the 6 pascals. So the answer, let's see if I can get this down here out the way. So the answer equals, down here, look, the answer was 207.8 times 10 to the 6 as a pascal, or because 10 to the 6 is mega, symbol for 10 to the 6 is megabyte. All right, you can do 207.8 megapascals. Pascalio, Joe Pasqualis. With what we're doing, stress should always be big. All right? If you're getting smaller answers, it's because you may have forgot the killer, or you may have forgot to do things with the meters. So the stress on that bar is 207 megapascals. Everybody all right with that? Type a dot. Type a dot. All right, that was page 6. This is going to be page 7 coming up. Right, so we've got that, right? 7. Let's go 7. So we know whatever this thing here was, it's been pulled apart by a force, and the stress on it is 207.8. So 207.8 times 10 to the 6 pascals. That's the stress, right, on this object. There's my stress. Right, now that's the stress caused by that force. Now we know that that stress will cause this length to go this way, right? Because it's right, it's an induced stress the length is going to stretch. So we're going to get a change in length. That triangle L just means delta L is change in length. All right. So same bar, say. So we may start off with a, I don't know, let's just say this was, I don't know, 1.5 meter long. 1.5 meters long. So it's a bar, I don't know, and it's 1.5 meters long with that force on it. So it's got 8 kilonewtons on it. The stress on it is 207.8. Now, what is that stress going to do? Well, depending on what material it is, it's going to make it, all right, change length. It's going to do this. It's going to stretch it. I'm going to give you a number. Let's just say it was 5 mil. So it's 1.5 mil, sorry, 1.5 meters long, and this stress here, this tensile stress, has made it change its length. So delta L just means change in length. That's all it is. Saves you writing change in length all the time. You can write X if you want. Just sometimes X can be multiplied by, can it? So we need to work out now, and they work this out using a strain gauge. That's how they measure things. Strain gauge. We need to work out now the strain. And the reason why we normally we measure strain using a strain gauge, and then we can go back and work out the change in length, but we'll go this way now. So strain, can anybody tell me what it was from this morning? Because we did it in materials, if you remember. Strain is going to be, anybody know? Anybody brave enough on a Friday afternoon? Half-term Friday afternoon? It's going to be change in length. It's going to be the change. There we are. Change. It's going to be the change, right, over the original. That's what it's going to be. And we know that we've done this. So the strain is going to be, right, delta L is the change in length. Saves you writing it all out, look. And the original length can just be L. That's L, yeah. So the formula to write down. We've seen it before. Right. Now strain hasn't got any units. There's no units. It's a ratio, really. It's a length over length. As long as they're in the same unit, same units. As long as they're in the same units, doesn't really matter with strain. They can be in meters, as long as they're both in meters, or they can be in millimeters, as long as they're both in millimeters. Makes a difference. It could be both in miles, as long as they're both in miles, or they could be both in inches, as long as they're both in inches. You get the same answer. Because normally the change in length is very small, like we've got here. We've only got 5 mil, and we've got this. So to find the strain, now I'll do both ways just to show it, right? I'll do it in meters and I'll do it in millimeters because you get the same answer. So the strain induced in this bar due to that force is going to be change in length over original length. So I'll do it in millimeters first, right? I'll do it in millimeters first. Millimeters first, just to show that you get the same answer. So the strain, the change in length over original length. So it's 5 millimeters divided by the length. Right, because we're in millimeters now, we're going to do this in millimeters. So how many millimeters is 1.5 meters? It's 1,000 millimeters in 1 meter. So to go the other way, just in case, to go the other way, you just do this. You times that, times it by 1,000, right? Just in case. So 1,500. So that'll give you the strain. All right, both in millimeters there now, right? So I'll share my screen again just so you can see. Just so you can. No. Right. Take presenter. Share my screen. Where's that? So we did 5 mil divided by 1,500 gives me that 0.003, say. Do it again. 5 millimeters divided by 1,500. 1.5 divided by 1,500 gives me that 1 over 300. Right, just all of that. Or we'll have 0.003 will do me. Stop sharing. Come here. So that was 0.003. That's the strain, right? You can do the same in meters. Right. As long as they're both in the same units, it doesn't make a difference. So the strain now in meters is going to be the same formula. The change in length over original length. So we've got 5 millimeters, and that's the same as this. 5 times 10 to the minus 3 meters. We're just doing that. 5 divided by 1,000, that's all that is. Divided by 1.5, because we can do it now. So this way is both in meters, just to show you can do it either way. So I've got 5 millimeters, which is that many meters, and I got that many meters on the bottom, 1.5. I haven't got to change that. Just to show you that you can do it both ways. It doesn't matter what, as long as they're both in the same units, you're all right. So I had 5 divided by 1,000 is that, divided by 1.5. So 5 millimeters in meters divided by that, which is a meter. Same thing. Or you could do this. You could do 5 divided by 1,000 to get that into meters, and then divide that by 1.5 meters. Gives you 0.003. So it doesn't matter which way you do it, as long as they're both in the same units. So the strain on this bar now, it's getting messy now. The strain on this bar is 0.003. It was 3.3333, right? That's the strain. Now normally you'd measure the strain using a strain gauge hooked up to a bit of electrical kit. And then once you've got the strain and you know the original length, you can then work out the change in length. So normally you'd go the other way. You'd measure the strain using a strain gauge, and then because you know the length, original length, you can then work out that. So that's stress and that's strain. Everybody all right? Is everybody all right? I'm going too slow. Am I going too slow? Is everybody all right? Right, we've done stress, we've done strain. 7, 8. Right, we've done stress. We've done stress. We've done strain. Right, stress is force over area. Force over area. Strain is change in length over original length. Oh, that's in pascals there, right? Pascals, no units. That's not noun its, right? It doesn't say noun its, it says no units. Can anybody tell me the last thing I'm going to work out? I know stress and I know strain. We have worked it out in materials. What's the last thing I'm going to work out? We haven't gone to ductility because we don't. The last thing, we know stress and we know strain, so we can work out another property of this material using that. We haven't got ductility, no. The thing we did before it. We've got stress and we've got strain. We need to know the elasticity of this material, so we're going to use Young's modulus. Now we don't know if this material has gone past, right? If it's, we're assuming now, right? We're assuming that this thing, for now, we're assuming that it's in within the elastic limit now. So we've got to assume quite a lot of things here. Assume within the elastic limit. We don't know what the material is. We don't know, right? We can then work out Young's modulus. So Young's modulus, how stretchy something is. The higher the number, the stiffer it is. That is E. Symbol is just E equals stress over strain. And the unit is Pascal. There's no unit down there, is there? So it's Pascal again. Something else to write down. All right. And now we can work it out because we've just worked out. We've worked out the stress on the previous slide and we've worked out the strain on the previous slide. So we can just divide them together now. So we know that E is going to be stress over strain. What's my stress? I need to go here. There's my stress there, look. 207.8 million. 207.8 to the 6. So 207.8 times 10 to the 6. It's my stress I'm looking at, and there's my stress here. We worked it out, 207.8. And then the last one to work out is strain, which we just did. There's my strain, 0.003. So we divide all of that by 0.003. Whack that in your calculator and you should get a number. So I'll share my screen just so we can see it. Let me write it down. 207.8 divided by 0.003. Obviously, if you did the strain calculation in 1 underneath it, it's a bit more accurate, isn't it? But I'll just use my rounded up number. So we'll take presenter. I'll share my screen. So it was 207. Let's go over here. It was, so you can do this, just do that. And do 207.8 times 10 to the 6. That's my strain. Divided by my stress, 207.8 times 10 to the 6 was my stress. Divided by my strain, which is this small number here, which we worked out. All of that. It's a big number divided by a very, very, very small number. So we should get a big number, which we do. All right. We like it in, threes. So press ENG. So it's 69 giga, because 10 to the 9 is giga, Pascal. So it's 62 sorry, 69.26 gigapascals. Right? So it's the stress over the strain. You could also go this way. You could do 207. You haven't got to do that way. Same way. 207, 6 equals that. Divide that by 0.003 equals that. There we are. Press that. Thank you very much. Stop sharing. So the answer for Young's modulus of this material, whatever the material is, was 69.26 times 10 to the 9 pascals. It's the same as 69.26 gigapascals. Tick. Da iawn. That means very good, Ashley, just in case you don't know what that is. Is everybody okay with stress, strain, and Young's modulus? Sort of. Did you follow on? Did you follow through? Well, if you didn't follow through, but you know what I'm saying. Why aren't I getting things? Can somebody just comment? Because normally I get a bell that lets me know. Oh, stop doing it. It's a bit odd. Normally I get like a bell. I get loads of bells now as you're doing that, but I don't get now. Perhaps they've stopped it. Oh, there we are. Oh, it's not working. Right, stop typing then. Oh, no, because like I say, it normally gives me a little bell. Right. Here's an example for you to do then. Now, it's the same way if it was compressive, right? It's the same way if it was compressive, so don't worry about that. Yeah, no, yeah, I have. I have them always down as pop-up alerts for chat, audio alerts for chat. It's on, but perhaps it's just, I don't know if it's about me. Like, it just, sometimes I like to know when people are asking me stuff. Is your computer muted? No, it's not muted. John, say something, John, because you normally say something. Say something to me.
Hey!
No, it's not muted at all. Right, here we go. Here's an example for you to do. Alright, 8. What's this one? 7, 8, 9. Same thing as before. Alright. So we need to calculate alright, stress, strain, and Young's modulus. Young's modulus. It's one word, right? Stress, strain. Here's my bar. Alright. Now it makes no difference if it's going up or down, right? It's the same thing. Here's my square bar. Make sure these lines are like, 30 degrees. Get it oblique, please, or isometric. That's my metal bar, or whatever it is. It's got dimensions, right? It's got dimensions of, right? So it's got 20 millimeters here. And this is also 20 millimeters. So it's 20 millimeters here and 20 millimeters there. Because it's a square bar now, right? It's a square bar. You need to find the area in a bit. Area of a square. So breadth times by depth, say, or width. Let's call it depth, I suppose. It's 20 by 20, right? But don't forget you need 20 to be in meters. It's a square bar. got a force on it, a tensile force pulling it here. Someone to give me a number. Someone to give me a number. 30 kilonewtons. Being pulled up 30 kilonewtons, right? This thing is a 20 by 20 square, and its length. Somebody give me a length. Obviously, this is not a scale now. This drawing, right? Somebody give me a length. 10. 10 what, John? 10 meters. No, don't do 10 millimeters. It's 10 meters. Not to scale, right? So I'm going to get some squash because my voice is going.
B and D stands for.
Huh?
B stands for.
The what?
And the A equals B and D. What does the B and the D stand for?
Breadth and depth. Like there, like breadth and depth of a square. So, or width and depth is up to how you call it. It's just 20 by 20. It's a square, that's all. Because this can be the height in it. So, all I'm trying to get at, John, is this. The area now is going to be, right? It's going to be 20. But you've got to divide both of these by 1,000 now. Because you've got to get them to meters. That's the, to make sure. Right. You can do 20 by 20 and then divide it by 1,000,000. That's one way of doing it, but don't divide the area by 1,000. You can't just work out the area in square meters and divide it by 1,000 because it's 1,000 by 1,000, right? So just for now, right, right, you got to divide the lengths by 1,000 first, then do that. So work out the stress for me, please. Force over area. Do that. Then do the strain. Right, hang on. I'm giving you a number. So this thing now is 20 by 20. I'll move the 20 over here now. So that's the cross-sectional area. Somebody give me a length that it's being pulled apart by. 7 millimeters. Or should we go for no? 7. That'll do me. So this thing, right, with this force, right, it's 10 meters long, but that force and that stress has made it stretch 7 millimeters. So the change in length is 7 millimeters. So work out stress, work out strain, and then divide one by the other to give you Young's modulus. We have made these numbers up, right? So if we're getting funny numbers, don't worry too much. But do the stress first, force over area. Don't forget 30 kilonewtons. The area you need to convert like this, look. Strain, you need to either be in meters or millimeters. And then Young's modulus is stress over strain. I'm going to get some squash, and I'll be back in 3 minutes. Right. As I say in EA Sports, back in the game. Back in the game. Is everybody alright? In the game, not back. In the game. Length is 10 millimeters. Change in length is 7. That's all I need.
What is the diameter 10, Morgan?
No, it's not. It's a square bar. It's not thing. It's a square.
So it's 20 or
It's 20. The area. That's this here. Look. Can you see? It's that cross-sectional area there. So it's the area of that square in there. Look.
Yeah, it's just that 20 divided by 1,000 times 20 times.
Yeah. It's 20. So yeah, you got to get into meters, right? So it's 20 divided by 1,000 squared, basically, isn't it? Is that
Oh,
area? That,
so the area is 400 times 10 to the minus 6.
correct. Yes.
Alright, cheers.
Because all you got to do really is you can 20 by 20, right, and then times that by 10 to the minus 6, because you're timesing 1,000 by 1,000. Yeah, but it's that square there. That's what it is, Jaden. Right? That's what it is. Has everybody got the? Can I change this now? This slide, so I can slowly work it. Do it for you. Well, I'll work it out now. So stress.
Yeah, can you go through it again more? Because I'm not really sure on this.
Come on, no problem.
I haven't got Scooby here.
Right, here we go. Ready? So there's my bar, right? It's been pulled up 30 kilonewtons. 30, 30, 30, 30. Right, so it's a square bar, just a square bar. It's 10 meters long. It's been pulled up by a force, whatever that is. Right, 13 kilonewtons. It's a square bar, so it's 20 by 20. So we need to work out the stress, the strain, the Young's modulus. The first one is the stress, which is just force over area. So we know that the force F is 30 kilonewtons. 30 times 10 to the 3 newtons. And the area is going to be this. 20 mil. Right? It's the area of that square, and it's 20 by 20, but you've got to convert that first. It's this length.
What's the length 10 meters?
Huh?
Or 20? What's the length 20 meters? 20 millimeters or 10 meters?
The length, the overall length is 10 meters. So there's my force. The area is going to be that square, so it's 20 by 20, but you've got to divide the 20s by 1,000 to get them into meters. Put that in your calculator, and it'll be 400 something, because it's 20 by 20 is going to be 400, isn't it? So, you know, don't double guess it, do 20 to, right? Because it's only the area of a square. It's only because we're converting it makes it funny. So you should get, for the area, you'll get this. 400 times 10 to the minus 6 square meters. See, what you can do is you can just multiply the millimeters together and just add that on the end. But just for now, just keep convert it from the start. That gives me my area, which now I can put here, because my force is 30 grams all over my area, which is 400 times 10 to the minus 6. It's going to be big numbers. Don't forget it's going to be a big number, because it's a big number divided by a small number. So in your calculator, do 30 times 10 to the 3, or 30,000, divide by 400 times 10 to the minus 6. Press equals. It's a big, big number, 75 mega. 75 megapascals, or don't write all of this in because you may forget a note. 1, 2, 3, 1, 2, 3. Do we all get 75 grands? 75 million. Right, Conahey?
Yeah. Cheers.
That's my stress. That's the stress. Alright. Done that. Tick. Strain now is going to be, as before, strain is change in length over original. So it's change divided by orig. Orig. Alright. Now we've got to be, so it's got to be in either meters or millimeters. Doesn't matter what it is with this, but as long as you're in both. Alright, if you're going to pick meters, both lengths have got to be in meters. If you're going to be in millimeters, both lengths have got to be in millimeters. Alright, so I'm going to stick with millimeters because I got 7 millimeters. Alright, and I got 10 meters, which is going to be 10,000. Because there's 10,000, there's a 1 meter equals 1,000 millimeters. I've got 10 of them, so it's 10,000. So strain change in length was, I can't remember now, what was it? 7 millimeters. And the length was going to be 10 meters, which equals to 10,000. Because this is 10 times by 1,000, which gives you 10,000. So you're going to divide that now by that, right? So you're going to divide that. All right, so we've got 10,000 now, because I'm going into millimeters now, right? I'm not going to use meters, I'm going millimeters. So my strain is going to be strain, different color. Strain is going to be change in length over original length. My change in length is 7 millimeters. My original length is 10,000 millimeters. Alright, we made these numbers up now, right? Because I'm in millimeters, right? I'm in millimeters. I'm in millimeters. 7 millimeters over 10,000 millimeters because it's 10 meters long. So do 7 divided by 10,000. Stupid number, really, isn't it? Really. Not much of a change, is that? So you should get this for your strain. 700 times 10 to the minus 6. Your calculator. Right, if you press ENG in a calculator, it'll put it in that format. Micro. Right, micrometers. Well, there's no units, but it's micro strain. Do we all get that for strain? 7 millimeters divided by 10,000 millimeters. Type a Z if you did. You may have done it meters. You may have got the same answer if you did it in meters. Makes a difference. Because you did 7 divided by 1,000 to get that into meters. And then you divided that by 10. You should get the same. Alright. That's my strain. Tick. Tick, 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 tick. And the last thing we've got to do is done the strain. The last thing we'll do is Young's modulus, which is stress over strain, which is back here somewhere. Look. No tricks in this. Stress over the strain. We've got the stress, we've got the strain, so there's no more working out to do. we've just got to use the numbers, hope they're right. So the last thing to do was Young's modulus. Modulus equals stress over strain. E is a symbol for Young's modulus. And the stress we've got is here, 75 megapascalios. So my stress is 75 mega, 75 times 10 to the 6. Alright, we'll use that. And my strain, which we just worked out, is here, very, very small, 700 times 10 to the minus 6. Right, so it's going to be a big number, this is. The higher the number, the less stretchy it is. This thing is 10 meters long, it's only stretched 7. So Young's modulus stress over strain, well, we know the stress is 75. 75 times 10 to the 6. All over the strain, which is 700 times 10 to the minus 6. Now, some of them may cancel out, you might see that. Still stick it in though. So 75, we'll make a big number now. 700 to the minus 6 gives you a very big number. You should get what you get. Somebody tell me. See if I'm right. You should get 107. If you cancel it, well, don't cancel them on because you'll have to add it back on again. Keep that in. 107.14 times 10 to the 9, which is the same as 17.14 gigapascals. Right. The higher the number, the less stretchy this thing is, or the stiffer it is. $75 divided by 700. Make sure you put in them and them. Is everybody all right with that stuff?
Yeah, I get it now, Mose. Thanks for that.
Well, it'll be a practice, that's all it is. So that's the Young's modulus and the strain and the stress. Alright, that's all we've got to do. Now, just one last thing. It's the same formula, really. It's the same formula for if it was compressive, but with tension, it's going in one direction. So it's like this stress would be in, you know, going up. So you would have a compressive stress going the other way. Obviously, it's not as easy because some materials behave differently in compression. But say if it was, you know, just assuming everything was the same, you'd have the same thing, but you could say it's going the other way. And it's 75 going up. But don't ignore that for now. Is everybody okay with working out then stress, strain, and Young's modulus?